In this video, we're going to continue our discussion of trends by looking into electronegativity. Just to go over a few learning objectives for the video, we're going to start with the definition of what electronegativity actually is. We should have already covered this in class, but I think reiterating it here in the video is not necessarily such a bad idea. We will then identify the actual trend from the plot, what happens to electronegativity going across the periodic table and what happens going down. And then we're going to go back and refresh some couple ideas. The rest of the video is going to be about explaining why electronegativity does what it does. We'll start by refreshing atomic radius and what Coulomb's law actually is, and then develop an actual explanation of the trend itself. And just like before, we're going to have an overall trend. This is what happens across and down, and then we're also going to address exceptions to the pattern. Certain elements don't seem to match the pattern, and as a result of not matching, they require explanation as well. To begin with, a definition for electronegativity is an attractive force an atom exerts on a shared pair of electrons. To represent this graphically, we can think of two atoms, atom A, and we can think of that atom as being chemically bonded to atom B. As we'll talk about in the next section, being chemically bonded together means that these two atoms are sharing a pair of electrons between them, and this is in order to gain an octet for both atoms, to gain a completely filled electron orbital. Now, unfortunately for both atoms, they're not interested in really sharing these electrons, but simply having those electrons to complete their individual octet. As a result, atom B will pull on these electrons in its direction. The force it pulls on those electrons with would be atom B's electronegativity, so we can describe this force here as being electronegativity of atom B. The force that atom A exerts then, which could be greater or smaller, would be the electronegativity that goes along with atom A. And the way I drew this, it shows atom B as having a bigger electronegativity than atom A does, and as a result we would expect atom B to pull these electrons around it more often than atom A pulls those electrons around it because of the difference in forces. You can almost think of this as like a tug-of-war match. The end result will be is that this molecule will have a negative side where the electrons exist more of the time and a positive side where the electrons exist less of the time. The end result being a molecule we would describe as polar. As I've already mentioned, out of the three properties we're going to deal with, electronegativity is probably the most significant of the three because it's going to play a role in this polarity concept, which is a big determining factor in the behavior of molecules. Let's start taking a look at the trend a little bit. Here we have the plotted data for electronegativity versus atomic number. When we take a look at these individual graphs, just like before, we will identify key points and then match those key points up to the actual periodic table itself. Before, we identified low points and we identified high points. And then we label these low points and these high points with respective elements. For example, the low points are all of our alkali metals, lithium, sodium, and potassium, whereas the high points in most cases are noble gases. In this case, noble gases do not have electronegativities. That accounts for the gaps in the graph, meaning these guys are actually our halogens. This is going to be the element fluorine, this is going to be the element chlorine, and this is going to be the element bromine. What we want to do again is match these up to locations on the periodic table. These elements constitute elements on the left side, fluorine, chlorine, and bromine constitute elements on the right side, and we can see as we go across the periodic table, in all cases we have a general upward slope, telling us that electronegativity gets bigger as we go from the left to the right of our periodic table. The other trend we can identify here is when we look at elements all in a row, and it's a little hard to see with the alkali metals, but clearer to see with the halogens here. If I focus on just fluorine, chlorine, and bromine, and I take some time to connect the dots between these elements, we see general downward slopes in each case, as a result showing us that as we go from the top of the periodic table to the bottom of the periodic table, we see our electronegativity get smaller. As we already said, these are trends you should have already identified in class, but to have this discussion, I feel it's very important to have these trends spelled out in advance. Just to summarize what we talked about in the previous page, you should be building a diagram, or I've already built a diagram similar to this one that highlights all three of our trends. Already on this picture, we see that as we go across the periodic table, atomic radius gets smaller, and as we go down the periodic table, atomic radius gets bigger. We're going to add in the new thing we just identified, which says then as we go across the periodic table, our electronegativity gets greater, it increases, and as we go down the periodic table, our electronegativity decreases. So we've added information to our summary chart. This chart again is what we will use when I ask you to put atoms into certain orders. For example, in greatest to smallest atomic radius, you would use this pattern, the elements on your periodic table, and you would fold all of that together into an order of atoms from largest atom to smallest atom. Alright, that enters the discussion of the actual trend itself. Now let's talk about the actual explanation. And to get into this explanation, as I already mentioned, there are some things that you need to remember. First of all is Coulomb's law. If you haven't already noticed, Coulomb's law is the underlying law that deals with all of this stuff. We think of the nucleus and the electrons surrounding it as being individual charged particles, and the forces exerted between them is described then by Coulomb's law. So again, Coulomb's law is the attractive force exerted between the charged particle. Typically, the property we're dealing with associates more with the force. The distance is associated very closely with atomic radius, and these two charges associate more with your nucleus and your electrons involved in the atom. So we can see how all of our factors kind of play in here. And we'll get into more detail with this in a second. The second factor we need to be aware of, as I've already kind of pointed out, is atomic radius. It basically determines, if you recall, it's the size of the atom. But another way of describing it that we kind of wrote down here was it determines how far electrons are on average from the nucleus. As a result, this atomic radius plays a very large role in the distance separating our two charged particles, our nucleus and our electron. The greater that distance, the impact it's going to have a bigger impact on the actual overall force. So let's start our actual trend explanation then. Across the row, as we go across the row, the distance separating electrons from the nucleus gets smaller. We already talked about from before, if we draw our little sketch of the periodic table here, that as we go across the periodic table, our atomic radius gets smaller. So what we're saying here is that the distance separating our electrons from the nucleus gets smaller, and as a result of that, the attractive force acting on those electrons gets larger. Just to put this in a little more perspective, that attractive force, as we already talked about, is determined by Coulomb's law. And that attractive force is electronegativity. If you recall the original definition, electronegativity is the attractive force an atom exerts on a shared pair of electrons. Basically what we can say from all this is that the smaller the atom, notice there's a smaller distance separating this nucleus from here than there is separating this nucleus from here. We can see, unfortunately, the equation I covered up here, as that distance gets smaller, the attractive force gets bigger. This atom can pull on that bonding pair of electrons with a greater strength than this atom can pull on that bonding pair of electrons. Therefore, those electrons will spend more of their time circulating this atom. Just to put some of that into words, smaller atoms pull harder on shared pair of electrons because of the smaller distance and the resulting larger force. And as a result, the smaller the atomic radius, the larger the electronegativity. And this actually describes the trend across the periodic table, and as we'll talk about in a second, it also describes the trend as we go down the periodic table. So continuing and finishing our trend explanation here, down a group it's exactly the same explanation as we've already pointed out. Going down the periodic table, atoms get larger and larger, meaning the value of D in these situations is going to get larger and larger as well. As the value of D gets bigger, the value of F necessarily gets smaller, and we said that F is really equal to our electronegativity. So larger value of D means a smaller force, which ultimately means a smaller electronegativity. Last piece of the puzzle then is to start talking about exceptions on the periodic table, elements that don't seem to match. If you recall, we've already identified exceptions with the elements boron, aluminum, and gallium on the atomic radius trend plot. The great news is that there really aren't any exceptions on the electronegativity plot. There are elements that don't match the pattern, but basically when atomic radius does not follow the pattern, i.e. the elements boron, aluminum, and gallium, electronegativity does not follow the pattern as well. And as I already said, in essence, there really are no exceptions here. This trend follows the atomic radius trend perfectly. I guess what I'm trying to say is the exceptions we do see in electronegativity are simply mirroring the exceptions we saw in atomic radius. So what we said before is absolutely true. As the atomic radius gets smaller, electronegativity gets bigger. As atomic radius gets bigger, electronegativity gets smaller. This is true for the general pattern, and this is true for the exceptions in the atomic radius plot as well. So the good news, no extra explanation here. It simply perfectly follows the atomic radius pattern. That brings us to the end here. Just to kind of give you a list of things you should be able to do now. You should be able to define the concept of electronegativity and what it is. You should be able to compare atoms and decide which ones would have greater or smaller electronegativities based on the location on the periodic table. This again is your ability to use the trend to organize atoms. We spend more of our time in class working on this, and we've talked about in the video. You should also then be able to explain the trend in electronegativity itself. What is the trend going across the periodic table and why does it happen? And what is the trend going down the periodic table and why does it happen? And then finally, you should be able to employ Coulomb's law and the atomic radius trend to support any of the explanations. And those can be explanations for the trend itself or explanations for the actual exceptions.